Let's take a look at Theorem 2.5. This is the limit of a composite function. Let's suppose that f and g are continuous functions such that the limit as x approaches to c of g of x is equal to L. And furthermore, let's suppose that the limit as x approaches to L of f of x is equal to f of L. Then we have the following statement about the composition. The limit as x approaches to c of f composed of g of x is simply equal to f evaluated at the limit as x approaches to c of g of x, which we know is equal to g of L. For example, if we take a look at this square root function here, we have the limit as x approaches to 0 of the square root of x squared plus 4. This is the composition of the function f of x equals the square root of x, with the inner function g of x equals x squared plus 4. We know the limit as x approaches to 0 of x squared plus 4. That can be found by simple evaluation. That's going to be equal to 4, because we can do direct substitution. Furthermore, we know that the limit at x approaches to 4 of the square root of function is going to be equal to 2. Therefore, we can do this one via direct substitution. This is going to be the limit as x approaches to 0. Actually, just go ahead and plug it in, because the limit of the inside part exists, and the square root function has a limit at that inside value. So this is going to be the square root of 0 squared plus 4, which gives us the square root of 4, which would be a limit of 2. If we take a look at part B, we can do the limit of the inside function. That's a polynomial. The cube root will be defined for any real number, and therefore we'll have a limit. So this one can also be done via direct substitution. The limit as x approaches to 3 of the cube root of 2 times x squared minus 10 is going to be equal to the cube root of 2 times 3 squared minus 10. This is going to be equal to the cube root of 3 squared is 9. 2 times 9 is 18. So we get the cube root of 18 minus 10. That's going to be the cube root of 8, which also has a value equal to 2. Let's find the limit in each example. One of the things that this example will teach us, and we'll see this kind of summarized in Theorem 2.6 in a moment, is that functions are pretty much the basic functions, your polynomials, your rational functions, your trigonometric functions, and your transcendental functions are all quote-unquote well-behaved, or what we're going to call continuous, at all of the points in their domain. So, for example, if we wanted to find the limit as x approaches to 0 of the tangent of x, the tangent of 0 is equal to 0, and therefore, because the tangent is well-defined and it's well-behaved at 0, we can do this one via direct substitution. We get the limit is equal to the tangent of 0, which is just 0. Similarly, if you look at part B, this is kind of using our composition theorem we just saw a moment ago. This is the composition of the function x squared with the trig function sine of x. Sine of x is continuous and defined for all real numbers, as too is x squared. Therefore, we can also find this limit via direct substitution. Everywhere we see an x, just plug in pi over 2. This is going to have the value sine of pi over 2 squared. We know that the sine of pi over 2 is 1, and 1 squared is equal to 1. In part C, this function is the product of x with e to the x, both of which are well defined for all real numbers. So we can find this limit via direct substitution. It's going to be negative 1 times e to the negative 1 power. We don't want to leave this with a negative exponent, so we're going to bring that e down into the denominator to make its exponent positive 1. And so as a limit, this one is going to be negative 1 over e. We have one more. This is the limit as x approaches to e of the ln of x cubed. X cubed is a well-defined function for all real numbers. The ln has domain x greater than 0, and because when x approaches to e, x cubed will approach e cubed, which is greater than 0. Therefore, this composition will be well-defined, and its limit is going to be equal to the limit. It's going to be the ln of e cubed. And then we recall from properties of exponents earlier, remember ln and e are inverses, so that should just return the result 3. To highlight some of the things we just saw a moment ago, Theorem 2.6 talks about the limits of transcendental functions. Let C be a real number in the domain of the given function, then any of our basic transcendental functions limits can be found via evaluating the function at that value in the domain. So for instance, the limit as x approaches to c of the sine of x would be equal to the sine of c. The limit as x approaches to c of the cosine of x is equal to cosine c. Where something's amiss here, this should be the tangent. Don't want to leave the tangent out. The limit as x approaches to c of the tangent of x is equal to the tangent of c. And same thing would hold true for the other three trig functions, your cotangent, secant, and cosecant, as well as any exponential function that's well defined, as well as any logarithm that's well defined. The next thing we're going to look at is a strategy for finding limits, and this is Theorem 2.7. This is a very powerful theorem, very powerful result that will allow us to find a lot of limits by hand without having to do a graphical approach or a table approach. We recall, and we made a big deal about this earlier, but we said that typically the limit as x approaches to c of f of x does not depend upon the value of the function at the point c. It's really only saying what the function values are doing nearby c as x gets closer and approaches to c from the left and from the right. Okay. Let's suppose that c is a real number, and let's suppose we have two functions that are equal to each other at all values of x except at possibly x equals to c in some open interval containing c. So what that means is, let's suppose we have on the x-axis here c. There exists an open set, it's an interval, let's call that interval I, such that for all x's inside of this interval, with the exception of possibly at c itself, f and g are equal to each other. If that's the case, and let's suppose further that the limit of g of x as x approaches to c exists, so if this limit exists, then it's also true that the limit as x approaches to c of f of x not only exists, but is equal to that limit as x approaches to c of g of x. And intuitively, this should make sense and agrees with what we talked about a moment ago. If f is equal to g of x at all values of x except for x equals to c, then if this limit exists, this limit should exist as well and have the same value. Let's see how we can use this to find the limit of the function in example 6. We want the limit as x approaches to 1 of x cubed minus 1 divided by x minus 1. Well, this is a rational function, and if we're not paying attention, we might just try our direct substitution. I could try to plug 1 in. It's worked in the past. It's been pretty efficient when it does. But if we do so, we're going to end up getting the value 0 over 0. Okay? And the reason for that is if we weren't paying attention, 1 is not in the domain of this rational function. So be very careful here. This theorem that we just had a moment ago, Theorem 2.6, but really even before so, it was Theorem 2.3 about rational functions, only applies to values of x, such that that denominator was not equal to 0. Here, this time, the denominator is 0 if we try to plug the 1 in, and we end up with the statement 0 over 0, which has a particular name that's called an indeterminate form. Let's be very precise about what this means in terms of the answer to example 6. Whenever you get an indeterminate form, in this case, the type we're going to see early on in the class is the indeterminate form 0 over 0. What that's simply telling us is that the limit cannot be found immediately via direct substitution. There may be a limit, there might not be a limit, but simply just plugging in the x equals to 1 in this case is not going to tell us what the answer is. So what we're going to do is we're going to exploit this previous theorem about the functions that agree at all values except for a single point. We can algebraically simplify this function by factoring. Okay. Maybe some of you haven't done this in a while, but x cubed minus 1, this is what we call a difference of cubes. And differences of cubes factor. This factors as x minus 1 times x squared plus x plus 1. And then this is all over x minus 1. So that difference of cubes in the numerator factors. And then what happens is, as a result of this, we can algebraically reduce this expression inside the limit because we have a common factor that cancels. So we get this simplification. This is the limit as x approaches to 1 of x squared plus x plus 1. And here's the beauty of that. This original expression we were not able to plug 1 into because 1 was not defined for that starting rational function. However, after we algebraically reduce it, so we know that this is true via algebra, and then this statement is true because this original function that we started with is equal to this function at all values of x except x equals to 1. The reason being the original was not defined at 1, whereas this reduced function is. Therefore, we can find this limit via direct substitution because, after all, this thing is just a polynomial. I can plug 1 in. I get 1 squared plus 1 plus 1, which is going to be 1 plus 1 plus 1, which gives us 3. And therefore, the original limit is also equal to 3. So very powerful technique. If you take a function and you can algebraically simplify it or reduce it, in this case, a common thing is what we call the dividing out technique. You cancel a common factor, and then you may get a simplified version that you are able to plug the limit into in order to find the value. So this is such a popular technique. It's given that name, the dividing out technique. Again, the form 0 over 0, it's what we call an indeterminate form. It doesn't mean that there's no answer. It just means that we cannot get the answer by direct substitution alone. Let's do another one of these. In example 7, we want to find the limit. If I try to plug negative 3 in immediately, we would have negative 3 squared plus negative 3 minus 6, all divided by negative 3 plus 3. That's going to give us 9 minus 3 minus 6 over 0, which is once again 0 over 0. So if we try direct substitution, we get that indeterminate form 0 over 0. Okay, so that's not going to help us. Let's try to see if we can algebraically simplify this function. It's another rational function. So you would want to factor the numerator and denominator completely. The numerator will factor as x plus 3 times x minus 2 divided by x plus 3. We do have a common factor that x plus 3 will cancel. So this is equivalent to the limit as x approaches negative 3 of x minus 2. And now to this algebraically reduced version of that function, this is something that is defined at negative 3. So now we can find the limit via direct substitution. Everywhere you see an x, put negative 3. This will be negative 3 minus 2, which produces a limit of negative 5. Another way to algebraically simplify some of these functions is to use the technique of rationalizing. And we can rationalize either a numerator or a denominator. Okay. In order to rationalize, what you would do is multiply by the conjugate. So if we have, let's say, the algebraic term a plus b, its conjugate is a minus b and vice versa. You're just changing the sign in between your two terms. If we take a look at example 8, here we're asked to find the limit as x approaches to 0 of the square root of x plus 1 minus 1, all divided by x. Let's go ahead and try the direct substitution route to see what happens. Everywhere we see an x, put a 0. This would be the square root of 1 minus 1 over 0, which is 1 minus 1 over 0, which yet again produces 0 over 0, that indeterminate form. So direct substitution does not give us the limit or tell us if a limit even exists in the first place. So the next step you go to is, well, so what do we do now? This isn't a polynomial or a rational function where you can factor anything. We could always resort back to, if we get stuck, a numerical approach, which can be cumbersome, or a graphical approach. But let's rationalize this numerator. So that's our brand new algebraic technique. The conjugate of the numerator is the square root of x plus 1 plus 1. So we're going to multiply this fraction by a form of 1. And let's see what happens. So this is the limit as x approaches to 0. A good tip, and this is a good idea to use from here on out, we weren't really too concerned with the denominator, so I'm going to leave the denominator in factored form. Do not distribute that x into those two terms. Keep it factored out for right now. Really, the goal was to rationalize the numerator, so we're going to expand the numerator. We will distribute this out. This will give us the square root of x plus 1 times the square root of x plus 1, which is the square root of x plus 1 squared. We get a positive square root of x plus 1, a negative square root of x plus 1, and then negative 1 times positive 1 is negative 1. Let's simplify this. This is the limit as x approaches to 0. The square root and the square cancel, so we get x plus 1. That square root and that square cancel. We have a positive square root of x plus 1 and a negative square root of x plus 1. They cancel. We have another negative 1 term up top. And this is all over x times the square root of x plus 1 plus 1. Now in the numerator, the positive 1 and the negative 1 cancel. So this is equal to the limit as x approaches to 0 of x over x times the square root of x plus 1 plus 1. And now that common factor of x cancels. So what we're left with, after we've rationalized the numerator, is this is equal to the limit as x approaches to 0 of 1 divided by the square root of x plus 1 plus 1. And this is an expression that is defined at x equals to 0. So now we can actually find the limit via direct substitution. Everywhere we see an x put a 0. This is going to be 1 divided by the square root of 1 plus 1, which is 1 plus 1, which is 2. So the limit in this one is 1 over 2, or a half.